Okay, let's get started. So, we finished chapter 1. Chapter 1, its main focus was introducing us to topological spaces, what a topological space was, how we can construct it from a basis, and then open and closed sets. So let's do a quick recap for the 10th time on what an open set is, and then a closed set follows real easily if we have a good understanding of an open set. So, I tried to write a little bit different each time to try and give you a little bit more insight. So we have some set X, right? A topology on X is a subset of the power set of X, satisfying these three properties. In other words, tau is a collection of subsets of X. It's a subset of the power set of X. It's a collection of subsets of X, satisfying these three properties. What are the three properties? The empty set and the entire set X are in tau, or in other words, they're open. If you have a finite number of sets in tau, then their intersection is, the intersection of all those sets is also in tau, or in other words, open. And if you have any arbitrary collection of sets from tau, then their union is also in tau. So the empty set and the entire set are open. Any finite intersection of open sets is open, and any arbitrary union of open sets is open. Closed sets are the complement of open sets, and so we showed that closed sets have these three properties, very similar. We showed that the empty set and the entire set X are always closed. We showed that if you have a finite number of closed sets, then their union is also closed. And then if you have an arbitrary collection of closed sets, then their intersection is also closed. Remember that? And the way that we got these from these just had to do with the fact that complement switches unions to intersections and intersections to unions. Right?
Yeah.
You complement this thing and you get this thing, where these are closed now instead of open, and similar from going from here to here. Make sense?
Right.
Okay. So, any questions about open sets and closed sets before we continue? Okay, so section 2.1, the big idea in section 2.1, well, we're going to define some more interesting sets that are open and closed, but remember that a topology is the minimum structure that we need to start talking about taking limits, to start talking about convergence, to start talking about continuous functions. A topology was the minimum structure that we needed to start doing those things. And we said that there's no reason for it to be intuitive that something satisfying these properties should give us those things. But rather, you just need to become really comfortable with these properties, and then we're going to prove that they have those things. So section 2.1, on top of introducing some more interesting open and closed sets that we'll talk about, we're also going to introduce the idea, finally, of a limit point, and taking the limit of a sequence and proving that a sequence converges, which is some basic stuff that you do at the beginning of calculus, right? So the stuff we do chapter 2 here, probably not that much different from what we do chapter 2 in calculus, except we're going to do it more generically in analysis. So that's what chapter 2 focuses on. Next week is when we'll actually be talking about limit points and converging sequences. This week, the big focus is going to be on the interior and the closure of a set. So what we're after is, if you give me, so if I know that X is a topological space, and if you give me some arbitrary subset of XA, I don't know if A is open or closed, it's just an arbitrary subset of X. With me so far? What we want to do is we want to associate an open set and a closed set with A. And we're going to sandwich A between an open set and a closed set. So we're going to define what's called the interior, A interior, and we're going to define what's called the closure, A closure, and we're going to sandwich A between them. We're going to make this a subset of this as a subset of this, and we're going to make this the smallest closed set that still contains A, and this is the biggest open set that you can fit in A. So it's like we're finding as close as we can, getting an open set that's as close to A as we possibly can, and a closed set that's as close to A as we possibly can. So even though A isn't open or closed, we're going to have associated open and closed sets with A, called its interior and its closure. And then we're going to prove some nice properties that these two things have. And that's what today's going to be focused on. So let's get an explicit definition for these things. So let A be a subset of a topological space X. So A is just a subset of X. X has a topology defined on it. All we know is that A is a subset of X. The interior of A, which we denote int parenthesis A, or just A with a circle above it. We'll use both these notations for whenever it's most convenient. So the interior of A, that should say of A, comma, denoted int A, or A with the circle above it, that's just an open circle, is the union of all open sets contained in A. A interior is the union of all open sets contained in A. Does that make sense? If you have an open set and it's a subset of A, then it's a subset of the interior of A. The interior of A is the union of all the open sets that you can fit inside A. All the open sets that are subsets of A. Union them all together, that's the interior of A.
Why not closed sets as well? Like, why specifically open sets?
It's just a definition, and then you'll see the useful properties it has.
Okay.
There's no way that I could just say, well, how can I make this appeal to your intuition? We couldn't easily capture the biggest open set that contained a certain set. I'll come back to that question with our picture and show you how it would be awkward to try and reverse these.
Okay.
Okay, so the interior of A, and notice also that we know that when we define the interior of A this way, is the union of all open sets contained in A. We know that the interior of A now is going to be open because it's a union of an arbitrary number of open sets. If I were to union up all the closed sets contained in A, I'm no longer guaranteed that that's a closed set. Because an arbitrary union of closed sets is not necessarily closed. It's only if it's a finite union.
Right.
So closed sets, we only know unions of closed sets are closed if it's a finite number. So here we have an arbitrary number, and so we're still guaranteed that this is an open set. So that's probably part of it. So that's what the interior of A is, and we also have the concept of the closure. The closure of A, represented CL, or A with a line above it, which is why we don't use this for a set complement. This means the closure of a set, is the intersection of all closed sets containing A. So the interior is the union of all open sets contained in A. The closure is the intersection of all closed sets containing A. So the closure is the smallest closed set containing A. The interior is the biggest open set contained in A.
Okay, so the closure is in X.
Yes, all these are in X.
Okay, and it's just containing A. It's the smallest closed set that contains A.
The smallest closed set that still contains A. Yeah, it only makes sense to talk about open sets and closed sets in the context of their subsets of X. So everything's a subset of X.
Right.
Okay. So that's the open set and the closed set. Not the open set and the closed set. The interior and the exterior.
Interior and closure.
And the closure. Thank you. The interior and the closure. Note, we already made this note that the interior of A is the biggest open set contained in A, and the closure of A is the smallest closed set containing A. And notice it is always the case that the interior of A is a subset of A, and A is a subset of the closure of A by definition.
Yeah.
Right? This is a union of open sets. This is a union of subsets of A. This is an intersection of things that have A as a subset. Make sense? Okay. So now let's do a feel-good example to try and establish some intuition for these things. Is that James?
What? Oh, yeah. He just wondering if you're coming.
Tell him to quit lying to you.
Okay. He's still at work.
Okay. So let's do a quick feel-good example. So imagine that A is this set. It's all the points inside this circle, including these points on the boundary, but not these ones. And it's got this weird panhandle coming off. So it's this line segment, these points, not these points, and then all the points inside.
Okay.
You with me? What's the interior of the scene? This is on standard topology on R2. Sorry. So we're talking about standard topology on R2. So what's the standard topology on R2? It's the topology you get when your basis is a set of open balls.
Yeah.
So any union of open balls, that's what open sets are. So if we were to look at all the open sets contained inside A and union them all together, we'd get just this open circle. That's the interior of A. And the closure of A, if we looked at all the closed sets containing A, we'd end up with this thing, the circle with that handle coming out.
That one's, how do you get the
Closure messes me up.
How do we what?
How do you get the other side of that circle to be close? Like, what is? Because I thought everything
Is it
contained in A
because-
was open sets, and now you're saying they're closed sets.
A is just a subset of X. It's
Okay.
just these points, not including these boundary points, and including this weird offshoot. It's just those points in R2.
Okay.
What is the interior of A? So A contains an infinite number of open sets inside of it, right? For example, this little open ball, that's inside of A. This little open ball, that's inside of A. What would we get if we unioned up all the little open balls that we could possibly make inside of A?
Yes.
We'd end up with this thing.
Yeah.
Right? Now, all the closed sets containing A, all we need to do is really convince ourselves that this thing is a closed set and we're basically done, right? Because then it's a closed set containing A. So let's look at the complement of this thing. What's the complement of this thing? It's all the points except for not those, and not these.
Oh.
That's an open set. Just that line segment's an open set. Union them together, that's an open set. So this is for sure a closed set.
Okay.
Is it just the outside or is it the entire middle too?
Inside too. Sorry. And this is the middle inside as well. So it's a closed ball with that one little offshoot.
Okay. Because its complement is open.
Yes.
Okay.
So notice it still contains every point in A, and it's a closed set. It's the smallest closed set you can possibly make, containing all of A.
Right, and you have to remember that it's an intersection.
Because notice this is also a closed set containing A. There's another one, all the points inside. So there's an infinite number of closed sets containing A. This is the intersection of all of them. This is what all of them have in common.
Oh, okay.
You can't make a closed set containing this and not get these points. And this is a closed set, so it's the smallest closed set. Make sense?
Yeah.
Yeah.
Why don't you have the line on that middle picture?
On this one,
Yeah,
like that.
well, it would be,
A dotted line means we don't include it.
So there's no point in putting it there.
So I could draw it like that, but that's the same as not having it there.
okay. You just, on the third picture, you drew a dotted line and called it an open set.
So on the third picture, that's because the points were on the outside. So when I drew my picture over here, that's a good point. Maybe that wasn't clear when I did it. So when we talked about the complement of this thing, we said it's the points out here,
So that,
not including this and not including this.
okay, but in that picture, that line is not an open set, right? Because if it is, then wouldn't it be in the middle picture?
This is not an open set.
Yeah, you said it was an open set, and it doesn't make sense to me why that's an open set.
Oh, sorry. Excluding this leaves us an open set, and then getting rid of this leaves us an open set. Intersect them together, yeah, an open set. Right? Everything but, in the standard topology, everything but this line, some line segment is opened. Right?
Oh, then maybe.
Half
I'm
plane,
missing
half
something
plane,
you're
half
saying.
plane, half plane. Intersect them all. So everything but this I probably said this is open. I meant everything but that is open. And everything but the points in here is open. So their intersection is open.
Okay, I see what you're saying.
Okay. Good question. Yeah, I probably said that wrong the first time. Because I don't remember drawing on the outside like I should have. But yeah, to complement that. Okay. So obviously we're not proving any of these. This is just to help give you intuition for what we mean by the interior and the closure. Good? Okay. So now theorem 2.2 has a bunch of parts, and we're just going to prove them one at a time, doing erase as I go. So let A, B be subsets of a topological space X. Then, if U is open and U is a subset of A, then U is a subset of A's interior. If U is an open set contained in A, then U is a subset of the interior of A.
Right.
Right? That one's almost trivial to prove. Second, well, maybe we'll prove these as we go. I don't even know if this one needs proved, because it's by definition. What is the interior of A? It's the union of all open subsets of A. U is an open and it's a subset of A. So it's in the interior of A.
Yeah.
Okay, so we won't bother proving that one. Next one. If C is closed and A is a subset of C, then A's closure is a subset of C. This one also just follows from definition, but for some reason it's hard for us to think about the closure than the interior. So let's say it one more time. Let's remind ourselves what this thing is,
What
and then
is
maybe you'll
C?
get it. What is the C is just some closed set, and A is a subset of C.
Oh, okay.
What is a closure? It's the intersection of all closed sets that contain A. C is a closed set that contains A. A closure is the intersection of all closed sets that contain A. So A closure is in C.
Yeah.
Does that one make sense, or do you write that one out more? Make sense? Or write it out?
Makes sense to me.
Make sense?
It's not as nice as the first one, but
Well, it's just going to be true by definition. Writing it out would be a two-step one, so maybe the definition of this is what's skipping your mind.
yeah.
A closure is the intersection of all closed sets. So if this is a closed set, this is a closed set, and this is a closed set, and A is right here, well, didn't draw a very good picture, did we? Let's go back to R2 to help us with our intuition. So we'll make A just an open set as well. So here's A, all the points inside of there, right? Here's a potential C. C is a closed set that contains A. The closure of A is when we fill in that line right there, right? Now there's A closure.
Oh, okay. Yeah, that's.
So A closure by definition is the intersection. Take all the closed sets that contain A, there's another one, there's another one, there's another one. Keep intersecting them, or taking the things that's always in all of them. And all you'll be left with is the closure of A.
Okay.
So by definition, the closure of A is a subset of every closed set that contains A. So if C is a closed set that contains A, then by definition of the closure, A closure is a subset of that set. Does that make sense?
Yeah.
Okay. Alright, so we'll do this one. So we'll go to 3. If A is a subset of B, then the interior of A is a subset of the interior of B.
Okay.
So 1, let A be a subset of B. 2, then notice that A interior is always open, right? So we know that the interior is an open set. So then A interior is open, and A interior is a subset of A is a subset of B. So it's an open set that's a subset of B. Therefore, A interior is a subset of B interior. What is B interior? It's the union of all open sets contained in B. A interior is an open set contained in B. Therefore, A interior is in B interior. This is a union of all open sets contained in B. This is one open set contained in B. We're really just using this,
Okay, yeah.
right?
Yeah.
Okay, so that's how that one works. This one, similar idea, but we'll write it out. So we're going to prove that if A is a subset of B, then the closure of A is a subset of the closure of B. So let A be a subset of B too. Then A is a subset of B is a subset of B closure, right? Because this is always true, and we were given this. And B closure is what? It's not open.
It's closed.
It's closed. So we have a closed set, probably should underline that, I think it's notation. We have a closed set containing A. What is A closure? It's the intersection of all closed sets containing A. Here's a closed set containing A. A closure is the intersection of all closed sets containing A.
Right.
Therefore, what?
A closure is a subset of B closure.
Perfect. Therefore, A closure is a subset of B closure. And we're done. Does that make sense? No questions? All right, let's do the next one. Okay. One direction, these is already done. We won't bother writing it out. So we're showing A is open if and only if it's equal to its closure. Well, notice this way we already have. If it's equal to its interior.
Okay.
A is open if and only if it's equal to its interior. Well, its interior is always open, so if it's equal to its interior, obviously it's open. So this way, we're not going to bother with it. We'll only prove this way. So, so we're only going to prove this direction. Let A be open. Now, what do I need to do to show that two sets are equal? I need to show that this is a subset of this and this is a subset of this. Observe that A interior is a subset of A by def, right? That's always the case.
Yeah.
So all I need to do is show that A is a subset of A interior. Since A is a subset of A and A is open, then A is a subset of A interior. What is A interior? It is a union of all open sets containing A. A is a union set containing, or A is an open set containing itself. Therefore, it's interior.
That seems weird.
Well, it's just a special case when it is its interior.
Yeah.
Yeah. It's not
So don't lose track of that we're talking about a very special case.
Okay, yeah.
When it's already an open set, then it is its interior. Draw in the open set in R2. What's the interior of that set? It's just a set. That's what we're saying. Therefore, they're equal, right? And we're done?
Mm-hmm.
So, I think we're good on that one, and we'll move on to the closed one. And the closed one, same thing, we're only going to prove this direction, because obviously if A is equal to a closed set, A is closed.
Yeah.
So we're not going to bother proving that way, we're only going to prove that way. So, let's see. 1, let A be closed. 2, observe that A is a subset of A closure by def. Right? So all we need to do is show that the closure of A is a subset of A. Now what is the closure of A? It's the intersection of all closed sets containing A. So 3, since A is a subset of A, and A is closed, then A is a closed set containing A. So then, a closure is a subset of A. A is a closed set containing A. The closure of A is a subset of every closed set containing A. Therefore, this is true. Therefore, they're equal and we're done. Any questions on those?
Very similar.
Bunch of, yeah, they are very similar. They're all relatively straightforward. Needs to get to the point where these appeal to your intuition. Because we're not really going to go back and reference this proof over and over again every time we use these properties. So, something that needs to appeal to your intuition as well as understand why I'm going through it. So, if there's any questions at all, anything that feels even a little bit weird, let's go over it as much as we need to. You're good? Alright. So, move the camera, finish up the whiteboard. Or chalkboard. I'll move it over to the other. Okay, so now we just have a bunch of examples using, I probably should have done this before Theorem 2.2, come to think of that. We're not really using this theorem over here, we're just doing a bunch of examples to help appeal to your intuition. What's the interior and what's the closure? So starting with example 2.1. So we're going to look at the interval from 0 to 1 including 0 in the standard topology on R. With me so far? What is the interior of that set?
The interval from 0 to 1,
Which interval?
not including 0.
The open interval from 0 to 1. That is the biggest open set you can get inside of there. If you unioned up all the open sets inside of there, you get this. You remember what the standard topology is on R?
Yeah.
It's all the open sets you can get by unioning open intervals. So does this one make sense? And then what's the closure?
She's close 0 to 1.
The closed interval from 0 to 1.
Okay.
Right?
Yeah.
That's the smallest closed set containing A. All we did to A was add a single point, so makes sense. All right, next. Once again, we're still going to have A equal including 0, not including 1 on R, but this time in the discrete topology. Remember, the discrete topology is a power set. So the open sets are every subset of R. So what is the interior of that set?
0 to 1.
It's just A. Same thing. That set is open. Reference over here. Let's see. If A is open, then it's equal to its interior. Okay. Even less than one references. What about its closure, though?
It's also A.
It's also just A. Remember, in the discrete topology, every subset is both open and closed.
Oh yeah,
Right,
that's
right.
right.
So that set is both open and closed. So it is its own interior and it is its own closure. Nothing wrong with that. Make sense?
Why do we care about the discrete topology for this weird things like this?
It's a fairly useless topology when it comes to capturing proximity. It's a good topology for corner cases to make sure students understand what an open and closed set are.
Okay.
So it's only useful for example problems and establishing intuition. But yeah, it has another name and it It is something like the useless topology, but I don't think it's that one I had. It's something like that. Can't remember it. Okay. Next. Same exact set, but now we have the finite complement topology on R. You guys typically struggle with this one.
Infinite.
Remember what the finite complement topology is?
It's something that has a finite complement, but
Right.
you write infinite up there. Or is that in finite complement?
In the finite complement.
Alright.
In the finite complement. So we have this in the finite complement topology. In the would have been helpful there. In the finite complement topology on R. So the only open sets in the finite complement topology on R are sets with a finite complement. Right?
Right.
Is the complement of this thing finite?
No.
So there's no way that you could union up sets that are bigger than this and get this thing, right?
What?
Yeah.
This set is too small to have a finite complement. It has an infinite complement.
Yeah.
You'd have to make it way bigger for it to only have a finite complement, right? So all the open sets in this topology are a lot bigger than this thing. So this thing can't be containing any open sets. In other words, assume that this thing did have an open set inside of it. Then that open set would have an infinite complement.
Which?
Restart. The complement of this thing is what?
Infinite.
Yeah, it's all the numbers from negative infinity to 0 and from 1 to infinity. So this set is not open, for sure, right?
It's close. Okay. Yeah.
Assume by way of contradiction that there was an open set inside of here.
Okay.
Any subset of this thing is also going to have an infinite complement. Right? If I make this smaller, or I just take a subset of it, the
Yeah.
complement gets bigger.
Yeah.
So, there cannot be any open sets inside of that. Right? Every subset of this has an infinite complement. In our topology, we only call a set open if its complement is finite. Every subset of this has an infinite complement. Therefore, no subset of this is open,
So the infinite.
except that. Because the empty set is a subset of every set, right?
But is it? Oh, yeah.
It's weird.
It
You
has
go
a
back to the
finite
basics.
complement.
Always open. And the empty set is a subset of every set, right?
Yes.
So you will always, at the very least, have the empty set as the interior of a set.
Okay.
Make sense? Now, the closure of A. Let's think for a second. If we're talking about the finite complement topology, then all the closed sets in this topology are finite, except for one. What's the only closed set that's not finite in this topology?
The entire set? Or
R.
R?
That's the only infinite closed set. Remember, what is a closed set? A complement of an open set.
Yeah.
We're talking about the finite complement topology. In other words, the complement of all our open sets is finite. So every closed set is finite, with the exception of R, because the empty set is still always open.
I don't see how A is in the closure. Isn't it?
This set's not closed. We need the smallest closed set containing this. All our closed sets are just a finite collection of points.
Which that is.
No, this is infinite. This is all the numbers from 0 to 1, excluding 1.
Oh, I see what you're saying.
Yeah.
Okay.
What's an example of a closed set in this topology? Here's an example of a closed set in this topology. 1, 2, 19 pi. That's a closed set because its complement is a set that has a finite complement. It's probably easier to draw the open set first and then see the closed set. What's an example of an open set in this topology? Besides the empty set and R. Those are always open. Okay, so excluding those two, what's another open set in this topology? How do you generate them? Start out with the number line. There's a number line. And then remove a finite number of points. So we get rid of u, and u. What points do we get rid of? We got rid of negative 19, negative 12, 0, 17, and 24.5. There's an example of an open set. Everything except a finite number of points. What's the closed set? The set containing negative 19, negative 12, 0, 17, and 24.5.
Yeah.
So all our open sets look something like this, with the exception of the empty set in R. So all our closed sets look something like this, with the exception of the empty set in R. All our closed sets are just a finite collection of numbers.
Yeah.
So how can we use just a finite collection of numbers to encompass an infinite number of numbers? All of the numbers from 0 to 1. We can't.
Right.
So this cannot be a subset of any of the closed sets generated this way. The only closed set that this can be a subset of is all of R. Is that making sense?
Yeah.
Let's look at it this way. This being closed implies what is open. So if this were closed, then this, negative infinity to 0, union 1 to infinity, would have to be open, right? But is this open? No. How do we know that this is not open? What's its complement?
Not finite.
This. Is this finite?
No.
How many things are in here?
A lot.
Infinite. How many numbers are there between 0 and 1?
Infinite.
There's an infinite number. So this set is not open because its complement is not finite.
Yes.
Okay.
Yeah.
So I can't use a finite set to encompass this thing. I can't have this thing being a subset of a finite set. So this thing has to be a subset of an infinite set. There's only one closed set that's infinite in this topology, and that's all of R. Because all our other closed sets are defined as a finite complement of an open set. Make sense? Am I stressing this too hard? We got it? Just move on?
I got it.
Okay.
Let's take a break from it, move on to this.
And then come back? Okay. We'll do that. Lower limit topology. So the lower limit topology was a topology whose basis is intervals where you include the bottom one and not the top one. So this is, the basis is like this. Lower limit topology. Your basis elements are like this. So any union of intervals like this. Right? So obviously this is an open set, right?
Yeah.
So we know that its interior is just A.
Yeah.
It is its own interior because that is an open set in the lower limit topology. But what's its closure?
I want to say it's 8.
Why do you want to say it?
Because all. I
What's
feel
the
like
complement of this thing?
it's just 2 of those.
The complement of this thing is
Infinity.
negative infinity to 0 union, oops, oh yeah, 1 to infinity, right?
Yeah.
Can I create this with a union of intervals like this? You're not sure?
Yeah,
You're not sure? Or are you saying, yeah, you can?
perhaps.
So if we do, so let's see, all the intervals, we'll say x to x plus 1. We'll union up all these for all x. We'll do n. We'll make these integers. So union up all the intervals like this, where n is in the negative integers. So we got union negative 1 to 0, negative 2 to negative 1, negative 3 to negative 2, negative 4 to negative 3, and keep doing that off to negative infinity. You're going to get this, aren't you?
Yeah.
Okay, so this is definitely open. Here's one way you can get it, right? Any arbitrary union of open sets is open. So union up an infinite number of open sets, still open. Okay, is this open?
Yeah.
Do we know that's open or are we guessing?
Yeah, that's open.
Yeah, that's open. We could do something very similar.
Yeah, I see.
From n to n plus 1 for all n in the positive integers. So 1, 2, 3. So from 1 to 2, 2 to 3, 3 to 4, 4 to 5. Keep doing that. Do. So this is open. So this is closed. So it's its own closure. Good there?
Yeah.
Okay. Now, back to the standard topology on R, and we're going to look at Q, the set of all rational numbers. You know what rationals are?
Yeah,
What?
everything that we put into a fraction.
A fraction of
2 integers.
integers.
Right.
Yeah. So any number that can be expressed as an integer over an integer, a over b, where a and b are integers. If I can express a number that way, it's rational. Okay? So we just have now the set of all rational numbers in the standard topology on R. Standard topology on R are open sets, are unions of open intervals.
Mm-hmm.
So what is the interior of Q? When you union up all the open sets contained in Q, what do you get?
Q.
You get nothing. Because for any open interval you take, A, B, and you guys probably don't know this, Emma does, but I don't know if you guys do. Any open interval you take is guaranteed to contain both a rational and an irrational number. So imagine that we zoom in on the number line. Here's the number line. A and B can be really, really close, but now we zoom in so that A and B look like this.
Okay.
It's guaranteed that somewhere in here there is a rational number, and somewhere in here there is an irrational number. So for any interval of numbers you take, you're going to have both a rational and an irrational. So every open interval is going to contain something not in Q. So no open interval is going to be a subset of Q. So when you union up all the open intervals that are a subset of Q, you've got none of them. So it's just the empty set.
Okay. Interesting.
Now let's look at the closure on Q. The smallest closed set containing Q.
R.
It's going to be R. Similar thinking, right? Good? Still, that's just an intuition thing. Hopefully we'll be able to prove this. It's the one problem I have in case everything doesn't take too long. Definition. So a subset A of a topological space X is called dense provided that its closure is the entire set. So what did we prove? We proved, not what did we prove, but what did we say up here? Up here we said that the rationals are dense in R. What that means intuitively is exactly what we said over here. What that means intuitively is any little open interval you take on the real numbers, you're guaranteed to have a rational somewhere in there. That's the intuitive way that we think about the rationals being dense in the real numbers. But that's its actual definition. Any questions?
Why is the rationals represented with a Q?
I do not know. We can't use R. And it's just what comes before the rails. So you have a Q.
Do you know what the proof is that for every A and B you have a rational and irrational?
Oh yeah, so probably should have said this. That is, the reason that we're not proving that in this class is this is a consequence of analysis. So in a real analysis course, when you do an analysis of just the standard topology on the real numbers, this is one of the things you prove. And, well, we have to use another proof to prove this. What we have to prove this is that for any number, real number x, if you do x to x plus 1, include on one side, don't include on the other side, you're guaranteed to contain an integer. And you get that from the completeness axiom.
So it's,
So
okay.
we'd have to work up to prove it in this class, which we don't want to do. But that's going to be like my second lecture in real analysis, probably something like that. No, it took us a while to get through the preliminary stuff. Was that preliminary?
Definitely wasn't in the second lecture.
It was later? Yeah, it was in chapter 1. So I think it took us 2 to get through. So either like lecture 3, 4, or 5. Can't really narrow it down. Seems like it should come relatively early. If you're really curious, I can find it for you
Okay, thanks.
after the lecture and then you can pull it up. Okay. It won't take long to find. Let's see. Okay, and then we were going to go back and talk more about the finite complement topology. Okay. Finite complement topology on R. So I'm going to draw some open sets and their corresponding closed sets. So here's an open set. It's missing this point. It's missing a finite number of points. So the closed set corresponding to this is the set containing, we'll just call this A1, A2, A3, and A4. Just the points it's missing. It has a finite number of them. So we'll even be more generic than this. Dot, 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 who knows which one we missed. All the way up to A sub n. So it's missing some number, A1, A2. We don't know how many, but whatever it is, it's a finite number. And it could be empty. It could be all of R, this could be empty, but this is the most points we could have possibly removed, a finite number. So this is the smallest open set we could have made. So this is the biggest closed set we could have made. Does that make sense? All our open sets are just removing a finite number of points for some finite number, n. So our closed sets are the complement of our open sets. So if our smallest open set, meaning the one that we took the most points out of, we took n points out of it, then our biggest closed set is going to be the one that contains n points, but still just a finite number. You with me? Now, notice what a closure is. It's the smallest closed set containing this. If our biggest closed set still only has n elements, and this has infinite elements, it's impossible for this to be a subset of something that looks like this. Does that make sense? So the only other closed set that we have that isn't like this is R. So in the finite complement topology, all our closed sets either look like this, or they're R, or obviously the empty set. So the empty set and R are always closed, and then all our other closed sets are like this. Since this obviously doesn't contain that, and since no set constructed like this contains that, then the only closed set that contains this is all of R.
I thought you said earlier the empty set is open. and then you just said
They're
that
both
the
open
open.
and closed.
Oh, okay.
Remember, it's just names. A set being open does not mean it's not closed. A set being closed does not mean it's not open. They're just names. A set can be open and closed. The empty set and the entire set that we're creating our topology on are always both open and closed. So maybe is that where the confusion was? Is there anything else confusing? Okay, so this is the smallest closed set that contains this, because all other closed sets don't contain that. It's the only one left. Okay, so we went back, made sense of that example. We defined.
Did you come up with a note yet?
Oh, the note. So the note is that, just making sure I didn't pass this proof without pointing out what we said. So here we showed that, not proof, example. Here we said that the closure of the rationals is all of R. So the rationals are dense in the standard topology on R. Similarly, the irrationals are dense in the standard topology on R. And you can actually get the irrationals real easy from the rationals. But it's not easy to see actually, unless I have the other proof written up, because it's just like a special case of it, so never mind. But it's a similar thing. For any open interval on the real numbers I pick, A, B, I'm always guaranteed that there's an irrational number between those. Okay.
How do you define an irrational number?
X is not in Q.
Oh, okay.
That makes it irrational. That's all it means. You're a real number that's not in Q. So the irrationals are just a complement of the rationals. Okay, so we covered the note, so we're ready to move the camera. Right? No more questions about anything on the chalkboard? Or are there? Alright. So let's move the camera. We got it wrong. And we'll see if this helps it not be so sensitive. Of course, maybe it's only me that it's ever bothering, since I'm the only one that goes back and watches these.
It's not true. I literally watched some things, so,
You did?
yeah.
Alright, guess I'm wrong. I'm hoping that stops from those awkward
Do
shakes
you
that happen.
go back and watch all your videos?
Yes, I want to know if I made any massive mistakes in what I was explaining to you so I can correct it the next week. Or to see if there's any obvious things that I should have done
Do
different.
you watch the whole thing?
Yeah, and I do that for discrete math and calculus as well.
Oh,
Impressive.
you watch 6 hours of YouTube videos a week. Gosh, Tony.
Well, I watch it on double speed, I don't watch it normal. Fortunately, I talk so slow that on double speed it's not bad. Okay, this is nothing.
That's a joke, that is not true.
Okay, so moving on. A lot of theorems now. Well, just 3 theorems, but one of them has 4 parts. And theorem 2.5 is like the capstone of this section. The one that we use most, but let's start here. This one's a real simple one. Theorem 2.4, we'll just do the proof over here. Alright, let A be a subset of a topological space X, and let Y be just some point in our topological space. So that's our givens. Here's what we're proving. Y is in the interior of A, if and only if there exists an open set containing Y, where that open set is a subset of A. Now, do you remember what an open set containing Y is called?
A neighborhood.
A neighborhood of Y. So I'm not going to bother specifying when I write something like this that Y is in that thing. When I write there exists U sub Y, then you instantly should interpret in your head there exists a neighborhood of Y. It's going to help me from having to write, not have to write this other stuff except for that U sub Y is a subset of A. So when I do it later, when I write u sub y, I'm just saying a neighborhood of y. And I'll reserve u sub y for that exact usage. Okay, so y is in the interior of A if and only if there exists an open set containing y that's also a subset of A. It can be an if and only if proof. And we'll see if you guys can do the first way on your own. So let's do this way first. 1. Let y in the interior of A. Now what am I looking for? I'm looking for an open set that contains y that's also a subset of A.
It's a union of open sets, so there's got to be one containing y. I don't know.
Yeah, you're overthinking it though. 2. Let u sub y equal A interior. Oh, there's an open set containing y that's a subset of A.
Crazy.
3. Then y is in u sub y is a subset of A, right? Alright. And the other way is a little bit more tricky, but still pretty straightforward, I think. So now, let u sub y be some open set such that y is in u sub y is in tau. So let u sub y be some set such that, not subset of A, right? Now we're going this way. So let u sub y be some open set such that this is true. Now I need to show that this is true.
U sub y is an open set within A, so by definition it's in the interior, and so y is also in the interior.
Perfect. 5. Since u sub y is in tau, since u sub y is open, and u sub y is a subset of A, then u sub y is a subset of A interior. A interior is the union of all open sets that are a subset of A. Right? Then y is in u sub y gives us y is in A interior. If y is in this thing and this is a subset of this, then y is in here. Right? Definition of subset. And that's it. Any questions? Anything weird? Pretty straightforward. All the above. Okay. 2.5. Now this theorem, 2.5, we are going to use all the time, left and right. And so you need to understand, I mean, we're going to use this thing like we've used the union lemma up till now. Remember how much the union lemma comes up? And I told you over and over again, you're going to need to make sure that this makes sense because we can't go back and reprove it every time you're confused.
Yeah.
Same thing with this. This is going to come up over and over again, and we can't go back and reprove it every time we use it. So we need to make this make sense. So maybe we'll start out with intuition and then do the actual proof.
Does it have a nice name like union lemma? Or?
No. Well, 2.5. Yeah.
Alright.
Alright. Let A be a subset of a topological space X, and let Y be any point in there. Then Y is in the closure of A, if and only if every open set containing Y intersects A. So let's make a picture just in R2 for a second to make this make sense. So here is a closed set, right? It's the border and all the points there. And we'll pretend that A was just the interior of this. So A was not including that. And then A closure includes the boundary. You with me so far?
Yeah.
So there's a hypothetical example. Now what I'm saying is that pick any point in the complement you want. So it can be a point in A or a point not in A, but on the boundary right here. That's still a point in A complement, right?
Yeah.
And I'm saying any open set that contains that point is going to intersect A.
Yes.
not only the closure of A, but it's also going to intersect just actual A. Let me draw this one more time. Try and use two different colors. So we'll make A is just going to be an open set to help make this more clear. So here's A.
Okay.
The closure of A is going to be including the boundary, right?
Yeah.
So here's a closure. It's a boundary and all of A, because A is a subset of A. So what we're saying is, pick any point in A closure you want. Let's start with the trivial point. Pick a point from here. A point that's actually in A. So we picked a point that's in A, not only in A closure. We're saying any point in A closure, every open set containing that point is going to intersect A. Now obviously if that point is in A, then every open set containing that point is going to intersect A, right? But now let's think about a point that's not in A but still in the closure. Okay, that's going to be a point like right there.
Can't you have it be on like the edges of another set? But it doesn't intersect. Like, can't you have that point be, because that point is not in A, then how, if you have another set that goes just on the, or that is just on the border of the other set, then how can it?
So this point right now is not in A, right?
Yeah,
But it's in A closure.
yeah.
So we're saying that a point is in the closure of A if and only if we can think of every open set, but in R2 we can just think about open balls. So it's in there if and only if every open ball I can create around that point intersects A. It is impossible for me to create an open ball around that point and not get a little bit of A.
Yeah.
Right?
Okay.
So when that's the case, then the point is in the closure of A. And if the point is in the closure of A, then that's the case. This is a one-to-one relation.
Makes sense.
That's the intuition for what we're talking about.
It doesn't have to be an open ball, though, does it?
No, it's just any open set. It's just open sets inside of R2 is unions of open balls. So it has to have at least one open ball in there.
Right.
So you can't create an open ball around that point without, you can't create an open set around that point without getting a little bit of A. It's impossible. So every neighborhood of that point, if we call that point Y, then every neighborhood of Y intersects A. So Y is in the closure of A if and only if every open set of Y intersects A, or every neighborhood of Y intersects A.
Yep. Makes sense.
Okay. Here's the way we would write that logic to help keep it clear. Y is in the closure of A is logically equivalent to, for all neighborhoods of Y, the neighborhood of Y intersected with A is not empty. Right? That's what we mean. If I say A intersects U of Y, what do I mean? I mean their intersection is not empty. That's what I mean by they intersect. There's something in their intersection.
Oh.
So this is the mathematical interpretation of what it means for two sets to intersect. Their intersection is not empty. Okay, now, here's what's even tougher about this theorem. When it comes up either this way, or it comes up using its contrapositives. So you also need to get comfortable with thinking about it in terms of its contrapositive. What's the contrapositive of this double implication? It's the negation of both sides, right? Remember that this right here, if we write it in A and B, that's A implies B and B implies A, right? The contrapositive of A implies B is not B implies A.
It's not being present.
Not A, thank you. And then contrapositive of this is not A implies not B. So this one we had here was A double arrow B is the same thing as this, but this is the same thing as this. This is the same thing as not A double arrow not B. Follow all that thinking there?
Yeah.
Okay, just basic propositional logic. So, Rather than think about it this way, a lot of the times we need to think about it this way. So let's go over it this way as well. If y is not in the closure of A, that's logically equivalent to there exists some neighborhood of y that does not intersect A.
Okay.
Yeah.
And that makes sense, right? If the point is over here not in the closure, doesn't matter how close you get it, as long as it's not in there, then there is going to be some open set that I can make around it so that it doesn't intersect.
Makes sense.
If you leave me any space, then I can use that little bit of space to create an open set and not get in it. Okay, that's the intuition. Turns out in proving it, this is easier to prove than this way, so we're going to prove it this way. But when we use it, we're going to go both ways, using it both ways. So very useful to get used to this theorem because, yeah, it comes up a lot. So let's prove it. I don't know if my black's going to stay good. Switch back to purple. So proof. I'm proving this. So we'll do this way first. Doesn't really matter which way we do first. Well, before I write that, I'll just write 1 and do my let. Oh, we already gave that as a given for the problem. Okay, so, sorry. Everybody's going to be writing the same thing over and over again. Okay, so assume y is not in a closure. What am I trying to get? I'm trying to get that there exists some open set containing y, such that when I take that and I intersect it with A, I get the empty set, and I'm done. So I need to find an open set containing y that does not intersect with A. Now, by defining it, well, there goes that. By defining it, we're going to give away the whole proof. Let u sub y equal the complement of the closure, and maybe end note, in case it's not obvious, y is in u sub y is in tau. So this is an open set, and this contains y. Right? Now, all that remains to show is that this is true. Right? Since A is a subset of A closure, then A closure's complement intersect A is the empty set. Everything in A is in a closure, so everything not in a closure includes everything not in A. What's a better way to say that? Let me try and come up with another way to say this. Everything in A is in a closure. So if we have everything that's not in A's closure, we don't have any of A.
Yeah.
Does that make sense? Maybe a picture real quick. Here's a potential A. We have everything that's not in A's closure. So here's a potential A. Here's A's closure. What's the complement of that? Not the the complement. That is everything outside the circle. And if we don't, or if our set looks like this, then we definitely don't have any of A. Because we don't even have A's complement. So we can't have A. So this intersection is empty. None of A is inside the complement of A's, I keep calling that A's complement, A's closure. Sorry. This is how we do the complement of sets in all other fields, and so I'm accidentally going to call this complement all the time. Don't let me do that. Otherwise I'll confuse you. This is a closure. Everything in A is in A's closure.
And the other one is the complement of the closure.
This is everything that's not in the closure.
Okay.
Why do we use that for closure and then in every other field they use it as complement?
Well, it's not that in every other field they use that as complement. It's just with the textbooks I am familiar with, they use this as complement. Bunch of different authors have their own personal preferences for how they do things.
Well,
Like this author loves to use x minus a all over the place for a's complement. And that just gets messy trying to keep track of. So I like to use this whenever I can, rather than having to write that as that. So in the author's proof, you probably have something like this: intersect A is equal to the empty set.
yeah, I see.
And this just reminds me to think about in terms of not. So not A's closure. Anyways.
Okay.
So I think that makes sense now, right?
Yeah.
Since A is a subset of A's closure, then everything not in A's closure everything that's not in A's closure has no elements of A. If we removed A's closure, we definitely removed A, so these two sets have nothing in common. So there, and so we're done, right?
Yeah.
Maybe a therefore. Therefore, u sub y intersect A is equal to the empty set. Okay, so we proved one direction, now we need to prove the other direction, right? So now, let's go this way. 5. What are we assuming this way? We're assuming this. So now, let u sub y be some open set such that y is in u sub y and u sub y intersect A is equal to the empty set. Right? So we just have some open set containing y that doesn't intersect A. I need to show that that means that y is not in the closure of A.
Yeah.
Okay. So let me think for a second. Let V equal u sub y's complement. So V is going to be a closed set, right? And y is definitely not in V, because y was in u sub y. How can I say this? 7. Since u sub y intersect A is equal to the empty set, then A must be a subset of u sub y's complement, which gives us that A is a subset of V. If u sub y and A had nothing in common, then everything in A must have been not in u sub y. Everything in A is in not u sub y. U sub y and A have no elements in common. So everything in A is not in u sub y. Everything in A is not in u sub y, or in u sub y complement. Same thing. With me?
Yeah.
U sub y complement, by definition, that's V. We know that V is closed. How do we know V is closed?
Because
Because
it's the
it's
complement
equal
of
to
y.
Complement is open.
Yeah, u sub y is open, so V is closed. So I found a closed set V containing A. So then what do I know about A's closure?
It's a subset of V.
Perfect. Then A closure is a subset of V. Where are we trying to get? I'm trying to
Y
get.
is not in A comp or A closure.
How do I know that Y is not in A closure?
Because Y is not in V.
Because Y is not in V.
Yeah.
So then A closure is a subset of V, comma. But since Y is not in V, then Y is not in A complement. And we're done. Any questions on that? Bless you. You sure? This is a proof that's never going away.
Kinda like it.
Okay. So if we're good with that, then let's move on to our next proof. Our next theorem, which is actually 4 proofs, and crank it out. And ignore these little scribblings here. These are like the mini epiphanies I had to have for each one to figure out how to do it. And in case I got stuck, I wanted to scratch them out right there so I didn't have to go look up how I proved it before. But worst case scenario, I can go find my proof. Okay. So, proof, and we'll start with the proof of 1. Let's read these real quick and make sure that they make sense. Let A and B be subsets of a topological space X, then 4 properties hold. The interior, so notice now I'm using this for the interior and this for the closure. Don't be confused by that. And the only reason I'm doing that is because this is kind of weird. Is that the interior of A closure, or A complement, or is that the complement of A interior? Because those aren't the same thing. So this is the interior of A complement.
Yeah.
This is the complement of the interior of A. Interior of A complement. Complement of the interior of A. And that's why I'm using that rather than this notation, because this is too vague. Okay. Here's basically what we're going to show. When you pull the complement out of an interior function, it switches it to a closure. And when you pull it out of a closure, it switches it to an interior. That's intuitively what you keep track of in your head when you actually need to use this down the road. But this shouldn't seem too intuitive, at least it wasn't to me just looking at it. It took me a while staring at it to make it make sense. So let's make it make sense. So we'll start out with some set A, and we'll stick with just some set like this. A, and we'll make some half circle in the standard topology. With me so far?
Okay.
What is the complement of that? A complement of this is going to be including everything on the outside.
Yeah.
So A was including things on the inside here. This is A complement. And then the interior of this is going to be that, right?
Yeah.
The interior of A complement. Now let's do it the other way. Once again, here's A. Over here, I need to write next the closure of A. So what's the closure of A? Here's A closure, points inside. What's the complement of that? It's this.
Right.
See how those are the same?
Yeah.
Okay. So that will be the first proof that we do. Maybe while we have these written up here, let's also do it the other way now. So using the same A, let's make sense out of the other proof real quick. I should have left that because we still need its complement. So this was A. A's complement we'll write over here. So right here is A's complement. the interior of A, we'll write over here. This is interior of A. And then, let's see, we take the closure of this thing. The closure of this thing is going to give us this, all the points out here, right? That's the closure of this. It's the outside points. And then the complement of this, we're just basically getting rid of the points inside this open circle, which leaves us this. So there's a little picture demo that they should be the same thing in standard topology on R. We'll do these proofs now. Okay, so let's do the first one. Showing that these two sets are equal, I need to show one's a subset of the other, and then vice versa. So I'm going to show that this is a subset of this. I'm going to grab an arbitrary x in there and show it's in here. With me?
Yeah.
So let little x in the interior of A complement. And where am I trying to get? Let's just keep it up here so I don't have to keep looking down there. I'm trying to get, it's in the closure of A complement. I'm trying to get x's in there. And then I'll have shown that this is a subset of this, and then after that I'll show this is a subset of this. Okay. So 2. Let's see. I know that the interior of A's complement is a subset of A's complement.
Yeah.
Interior of A's complement is a subset of A's complement. So that gives me that since x is in here, and this is a subset of A's complement, that gives me that x is not in A.
Yeah.
Let me think for a second. X is not in A. Sugar. How am I going to show that x is in the closure of A complement? I'm going to do this by showing that x is not in the closure of A. So if I've shown this, I've shown this. X is not in the closure of A. Oh, duh. Sorry. Use the proof that we just had. So the interior of A complement is a subset of A complement, right? So interior of A complement intersect A is equal to what?
Interior of a complement.
Intersected with A.
Oh, I thought you said a 0.
The empty set.
Can't be just like.
Yeah.
If everything in the interior of A complement is not in A,
Yeah.
then when you intersect with A, you get nothing. So then by 2.5, x is not in A complement, which gives me x is not in the closure of A, which gives me that x is in the closure of A complement. Right? Sorry. This is open. I didn't point that out explicitly. This is an open set. Right? This is an open set containing x. So I found an open set containing x that doesn't intersect A. If there exists an open set that doesn't intersect A, then that point is not in the closure of A. There exists an open set that does not intersect A, so X is not in the closure of A.
Yeah.
So X is in the complement of the closure of A. These are logically equivalent statements. Is it weird that I'm switching between the CL and the overline? So X is in A closure's complement. If X is not in the closure of A, then X is in the closure of A's complement. And that's the exact same thing as the closure of A's complement.
Yeah.
All make sense? Okay. Therefore, interior of A complement is a subset of the closure of A's complement. Now we need to prove that this is a subset of this. Right?
Yeah.
Okay. So that's one way. 5. I need to show that the closure of A complement is a subset of the interior of A complement. Okay, so since, will you guys be okay? I don't want to keep writing it out like that. You okay with me writing it this way?
I actually like that way better for some reason. I don't know why.
Okay, so I'll do this one. With the interior is the only one where it's hard for us to tell what order they go in. But here it's easy to do the order because I can write it this way when it's A closure complement versus A complement closure. Make sense? So, yeah, we'll do it this way. So now I need to show that this is a subset of this. Since A is a subset of A closure, then A complement is a subset of A closure's complement. Nope, other way around. Nope. Yep, other way around. Sorry. Is that right? Since everything that's in A is in A complement, then everything that's not in A complement is also not in A. Right?
Yeah.
So yeah, that's right. Now what do we know about this set?
I'm assuming it contains X, even though, is that?
We haven't defined an X. We restarted. Ignore the X. That was only for the first part.
It's open.
It's open! It's open and it's a subset of what? A complement.
Open is a subset of A complement.
Yeah. Since A closure complement is open and A closure complement is a subset of A complement, then A closure complement is a subset of what? The interior of A complement. What is the interior of A complement? It's the union of all open sets that are a subset of A complement.
Oh.
This is a subset of A complement that's open. Right? And we're done. Well, we can write one more line. Therefore, A complement or A closure complement is equal to the interior interior of A complement. They're equal, they're the same, which is what we're trying to prove. Good?
A closure complement is a subset of the interior of A complement.
Yes. So let's say this one again.
The
It's going to help when you say it in terms of not. So A is a subset of A closure. So everything not in A closure is also not in A. If it's not in A closure, then it's not in A. Everything in A is in A closure. So if it's not in A closure, it's for sure not in A.
yeah.
More? Let's ignore this and just say, look at this. Everything in A is in A closure. So everything not in here is definitely not in here. That's what that says.
Okay. That makes sense here.
Good? Alright. That finishes the proof of one. Next. Don't worry, the last two on this are real easy. But this next one is the weirdest one. So, see if I can figure it out. I may have to go look at my proof. You guys can help me. We'll be fine. So now we're proving two. I just can't write what we're proving up here because I happen to look down here and keep finding it. We're saying that A complement closure is equal to the interior of A and then complement it. Or maybe this, should we use, maybe you guys will like this notation better. If we do A interior and then complement it on the outside like that. Do you like that better?
Sure. It works.
Good?
Sure.
Yeah.
Yeah, man. Just whatever helps you more. Okay, so one. First way. So we need to show that the closure of A complement is a subset of the complement of A interior. So, I'm thinking like middle steps. I know that this is going to be a closed set, right?
Mm-hmm.
And this is the smallest closed set containing A complement. So I want to show somehow that A complement is a subset of this thing, and we're done. That's big picture what I'm kind of thinking in my head.
And they're both closed sets.
Now since A interior is a subset of A, similar thinking to what we just did before, then A complement is a subset of A interior complement. Let's say it one more time, looking at this for a second, and then we'll look back over there. Since everything in the interior is in A, everything not in A is not in the interior.
Okay.
Follow that? Then, I always want to put this side, but it goes above it. So then, the interior of A complement, or the complement of the interior of A, I should say, then the complement of the interior of A is a closed set containing A complement, right? We should show that A complement is a subset of this thing, and we know that this thing's closed. How do I know that this thing's closed?
Because it's the complement of an open set.
It's the complement of an open set. A interior is open, so its complement is closed.
Yeah.
So I found a closed set containing A complement. Right?
Mm-hmm.
Therefore, the closure on A complement is a subset of that closed set. the closure on A complement is a subset of any closed set containing A complement. This is a closed set containing A complement. So the closure of A complement has to be a subset of that. Does that make sense? Anything weird? Okay. Now let's see if we can do the other way. So for let X in the interior of A complement, and just to help me think, that's the same thing as X is not in A interior. So I'm trying to show that X is in A closures, or A complement's closure. So I need this. So let's just do that and then create some arbitrary set containing it. And let U sub X be any open set containing X. So we're going to ultimately use this proof. What I'm going to do is I need to show that any open set containing X, for any open set you find, it intersects A. Therefore, X is in A closure. So I need to show that for any U sub X you choose, any open set containing X, I need to get U sub X intersect A complement is not equal to the empty set. If I can get this, then I will know that X is in A complement's closure. Just making sure you understand how we're going to use this theorem. Okay. Since how can I say this well? Since A interior is a subset of A, comma, then A complement is a subset of A interior's complement, right? If the interior is a subset of A, then everything not in A is not in the interior, which gives me that X is in A complement. So I know that X is in this sink. This is a subset of this sink. Oh.
Yeah, it doesn't work.
That doesn't work. Oh, I'm working too hard. I'm trying to get, X can't be in that because X is going to be in this. What am I doing? Oh, no, it still could be. Let me see. Let X be in the complement of the interior of A, and let U sub X be any open set containing it. I need U sub X intersects A complement. And I get that if I get X is in A complement. So let's see. not in the interior of A, subset of A. Let me see what I have written over here. Look at my little epiphany moment. So I have X is not in the interior of A, which gives me that is that U sub X intersect A is not equal to the empty set. No, I said U sub X is not a subset of A. How do I know that? All right, let's look at my proof. To prove let X in the interior of A's complement and let U sub X be any open set containing X. Observe that since X is not in the interior of A, then U sub X is not a subset of A. How do I get that? Oh, because U sub X is open. Okay. So what I have written there is perfectly valid. Jeez. Okay. So since X is not in the interior of A, and X is in U sub X, and U sub X is an open set, U sub X is not a subset of A. Because if U sub X were a subset of A, since it's open, U sub X would have to be a subset of A interior. But it can't be because A contains X, which is not in A interior. Do you follow that thinking?
Yeah.
Okay, so then U sub X is not a subset of A. So it has something that's not in A. So then U sub X intersect A complement is not equal to the empty set. Which gives us that, this one, which gives us that X is in a complement closure, which is what we're trying to show, right? So that gives us that A interior complement is a subset of A complement closure. Okay, so let's make sure this makes sense. So, once again, I know that U sub X is an open set and it contains X, right? And I know that X is not in the interior of A. If U sub X was a subset of A, then since it's open, U sub X would have to be a subset of the interior of A. But it can't be because it contains X, and X isn't in the interior of A. So I know that U sub X is not a subset of A. So I know that U sub X has something that's not in A, or in other words, U sub X has something that is in A complement. So when you intersect U sub X with A complement, you get something. It's not the empty set. You get something. And so if, and remember, U sub X, all we knew about it was some open set containing A. So we showed that for any open set you have containing X, U sub X intersect A complement is not empty. Therefore, X is in the closure of A complement.
Yeah.
And we're done. Okay, there we go. Got that proof. Make sense? And now the next two are real easy. So, proving 3. So we want to show that the interior of A union with the interior of B is a subset of the interior of A union B. That's what we're trying to prove. Okay? Observe that A interior is a subset of A and B interior is a subset of B. So A interior union B interior is a subset of A union B.
Yeah.
Since A interior union B interior is open, then A interior union B interior is a subset of the interior of A union B. Is what we're trying to show.
Yeah, that's pretty straightforward.
That one's pretty straightforward. Now this is just a subset, not an equal. We'll show it's not an equal with counterexample. Let's look at A equal to, how do I want to do this? I think I want to do 0, 1, and B is going from 1 to 2 in the standard topology on R. You with me?
So you're still in part 3? You're not moving on to part 4?
Yeah, still in part 3. So we proved that this is a subset of this. You'll notice on the next one we're going to use an equals.
Yeah.
So I'm just going to show you why this isn't an equals with a quick counterexample.
Okay.
So we have A and B in the standard topology. A union B then is what?
It's just
0
0
to 2.
Like that, right?
Yeah.
But the interior of A interior is 0, 1. B interior is 1 to 2. But the interior of this thing is the entire set 0 to 2. So notice that these two union together don't include 1. This one does include 1. So they're not the same. This is just a subset of this. So a quick counterexample so they can't be equal, and we prove that they're a subset. Good? Okay, now the last one. We're going to prove that one's a subset of the other. The first way is trivial, but we'll do it anyways. One, observe that it's going to be the exact same thing almost. A interior is a subset of A. Oh, we're intersecting. And B interior is a subset of B, so A interior intersect B interior is a subset of A intersect B, right?
Yeah.
And now, this is obviously an open set. It's an open set contained in there, therefore it's in the interior of the scene. I don't even know if I need to write that. Good with that? So now we'll just skip to the other way. So 2, blah, 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 3. So now we need to show that this is a subset of this. Let's see, how did I do this? Let's just read it real quick. Okay, so let x in, let's see, which way didn't I go? I need to go this way. So let x in here. So let x in the interior of A intersect B. And notice that that gives me that there exists some open set u sub x such that u sub x is a subset of A and u sub x is a subset of B. I didn't even need to come up with a u sub x. I could have just said this thing. The interior of A intersect, but this works too.
Okay.
So, but if it works for this, definitely there has to be some open set containing it that's in the intersection of these two things. So then there exists an open set such that that and that are true. Then u sub x has to be a subset of A interior, and u sub x has to be a subset of B interior. Therefore, u sub x is a subset of A interior intersect B interior, right? If it's an open set contained in A and it's an open set contained in B, then it has to be a subset of A's interior or B's interior. And if it's a subset of both those, then it's a subset of both those, right? And now, since I did the stupid and didn't just use this for u sub x and we use the union lemma, I can do this for any x in there. For any x you pick, I can find an open set containing that x such that this is true, therefore they're equal. Oh, I don't even need to think about that. Therefore, u sub x is in there, which gives me x is in there. That's easier. So x is in there. So every x in there is in there, so it's a subset. And we're done. Make sense? Okay, that's it for chapter material. Next week we'll move on to talking about limits.
Is that the whole chapter?
Not chapter, sorry, section. That was section 2.1, the section entitled Closures and Interiors.